Hello students and welcome to the Spectrophotometry Lab Writing Up and Calculation. I'm going first to start by reminding you of what we have done. In part 1, we have discussed how to choose the best wavelength for both the red dye and the yellow dye. And what we did, we have scanned both dyes and looked at how they overlap together, where here we had absorbance and here we had wavelength in nanometer, and this was the visible spectrum. And for the red, we had no problem identifying the peak, as it has like almost minimum, I can consider it like zero overlap, and that was almost around, I would say, 5-10 nanometer. And then for the yellow, we picked something on this side, maybe closer to 400 nanometer, where we still have high absorbance for the yellow but low interference with the red. Okay, so that was the other wavelength that we chose. We chose two wavelengths. This one best for red, this one was best for yellow. Now we also, as we were trying to figure this out, we have made different solutions of the red dye and the yellow dye. We have indeed made 5 different concentrations. And on those 5 different concentrations, we started all the way from 1, 0.80, 0.60, 0.40, 0.20 millimolar. And we have learned how to do this in the lab. We started from our stock solution in the lab, which had a concentration of 10 millimolar. Then we made our own stock solution that had a concentration of 1 millimolar. That allowed us now to block all our numbers in Excel and create the following. We have created 4 graphs. 2 of them were created for the red dye, and 2 of them are created for the yellow dye. Those are the standard curves that we created. For the red does absorbs around 510 nanometer, and it also absorbs around 400 nanometer, or whatever wavelength you decided or we decided we will use for either color. So for the red, we had a high absorbance at the 510. If we plug the absorbance versus the concentration in millimolar, starting from 0 all the way here to 1 nanometer, then we will have certain curve going almost this way. We can ask Excel to give me the best trend line and show the equation. There will be a linear equation created. Also, you want to notice that the slope here will be close to 1. Okay? Now, because the red does absorb less significantly at the 400, it will still give me a linear relationship, again, between absorbance and concentration. However, it will definitely have a lower slope, okay, because it doesn't absorb as high. Yellow almost absorbs nothing at 510 nanometer and absorbs significantly high at 400 nanometers. So you're going to have the graph here, that's almost gonna look like this, right? Because it's like no absorbance, almost zero, so it's almost zero slope. And then you will have the other one, again, absorbance and concentration, absorbance and concentration. And you will have here the high absorbance with a slope almost equal to 1 for the yellow. So you're gonna get, I would say 3 practical standard curves for your work after you are done. Now that we have those here, we want to remember something, which is Beer's law, which is the equation behind that linear relationship, which says absorbance equals K, B, C. Now, we are having to find out K for our equation. For all of our measurements, B is the length of the cuvette here, the path of the light, and that was 1 centimeter for all of them. Okay? Now, that means that if you look at your equation or the linear, which is the linear equation here, y equal this, 1 second please, so y equal mx plus b, right? So you will see that the slope here should be almost equal to K, right? Because the absorbance is Y, the concentration is X. This is, as I said, the value is 1 centimeter, so that means that the slope here will be equal to K. So if I go back here, you can get K here. I'm going to call this K red at 510. You're going to get K here, which is, I'm going to call this K red at 400. You're going to get K here, and I'm going to call this K yellow at 510, and another K here, which is K yellow at 400. Okay, so that takes me now, I have created all my standard curves, and I am ready right now to solve my unknown. My unknown, as a reminder, is a mixture of red and yellow. If you go back to the first part of this experiment, you will remember that it did look something like that, right? And what you accomplished in part 3, you have the measurement. You took this mixture, which is the unknown, and you did report the absorbance at 510 nanometer, and also reported the absorbance at 400 nanometer. So now you have your unknown absorbance at both wavelengths. Let's go back to these wavelengths, right? So this is here the first one, and this here is the second one. At this wavelength, which is like the 510 nanometer, the only thing that absorbs is the red color. So all the absorbance here of the unknown, because I am measuring it at 500 nanometer, only comes from red, because yellow almost zero here. It doesn't absorb, right? Yellow is almost zero. So what does that mean? That I can say, let me have a place to write this down. I can say that unknown absorbance at 510 equals absorbance of the red dye in unknown. And remember, you took your unknown and you do have that absorbance. So let's put a number to it, okay? Let's say that the absorbance for your unknown at 510 nanometer was 0.710, okay? So remember, absorbance equals absorbance of the unknown equals the absorbance of the red dye in the unknown plus the absorbance of the yellow dye in the unknown. Now, let's go here. At 510 nanometer, absorbance of the unknown will equal, as we said, absorbance of red plus absorbance of yellow. We did agree that we're going to consider this to be what? 0. So it will be the absorbance of the red. I do have this value. I have it. It was 0.710. Now, what is the absorbance of the red equal to? It equals K of the red at 510, because remember, I have 4K values. I have to choose the right one, times B, which is 1 centimeter, times the concentration of the red. Now, this is 1 centimeter. I know what it is. This is I got from my standard curve, and this is given also because I measured it. So now you can calculate CR, and what CR is the concentration of the red dye in the unknown sample. Okay? So now you have half of the unknown solved, which is I wanted you to tell me what is the concentration of the red dye in your unknown. Let's go back to our diagram. At 410, at 400 here, I can't just say, because this is the yellow color, I can't say that only yellow absorbs, also red absorbs. What does that mean when I write my equation? I'm going to say at 400 nanometer, the absorption of the unknown equals to the absorption of the red plus the absorption of the yellow. Let's say this is something you measured, you have this value. So let's say that when you took your unknown and you measured absorbance at 400, that this value was 0.523. Okay? What does that mean? It means 0.523 equals to the absorbance of the red at 400 equals K of the red at 400 times B times the concentration of the red in my unknown, plus the absorption of the yellow equals to K of the yellow at 400 times B times the concentration of the yellow in my unknown. Let's see what we have and what we don't. This is measured. This I get from my standard curves. B is 1 centimeter always, right? So B always 1 centimeter measured. Concentration of the red in my unknown, I just solved that in the previous slide, right? This is the concentration of the red. I have that value. K yellow at 400, I have that from my standard curve. B is 1 centimeter. So now concentration of the yellow, which is the only thing I don't know, is solved, right? So now you can tell me what is the concentration of the yellow in the unknown. And this is how you do the math to solve the concentration of both the red dye and the yellow dye in your unknown. Having done that and having said that, you are done now with all the mathematical component of this lab. What I want to explain next is the write-up for this lab. This is a typed lab report. So when we are going to write it up, we're going to have a cover page. In this cover page, I need you to have the title, and I need you to have the name of your name and your partner name, because you are going to partner up with a student and exchange data with, and also will be your section number. Okay, now then I want you to number all pages, and I want you after that to have table of contents, right? And there is also a document in your module that shows you all the things needed to write an appropriate lab report. And this here you will discuss what it is. Like we will be dividing the lab reports into part 1, part 2, part 3. Within part 1 there is data, there is calculation, so you're going to tell me the contents and at what page I can find them. Then after that, in a new page, you're going to start with introduction. And in the introduction, you are going to be talking about spectrophotometry in principle. What is it entitled of? What does it mean? And what kind of application we have when it comes to everyday life. It's like no more than one page. Then after that, in a new page, you're gonna start part 1. In part 1, every part you start, I need the objective. And the objective, if I want to simplify it for you, it is what I did and why I did it, right? So in part 1, we screened the red dye against the visible spectrum so we can find out the best wavelength that has highest absorbance and lowest interference. This statement that I just said, I explained what I did and why I did it. Okay, so this is the objective. Then after that, I want you to talk about the procedure. What did I need to do and how I did it to get this part done, and this is what you will see in that video in your module for part 1. And then we don't have data and math to process in this part, so you will end up having conclusion, and in our conclusion is the 2 wavelengths that we ended up choosing and why we chose them. However, before the conclusion, sorry, I forgot to say this, there will be data, right? And in the data, I would like to see the diagrams that shows the overlap of both wavelengths on top of each other, drawn by Excel. When you draw any diagram in Excel, I want the x-axis and the y-axis to be labeled properly. The y-axis is absorption. This is here is wavelength in nanometer. It would have to be graduated, starting from whatever wavelength the data start, ending where they ended, and make sure that the scale is appropriate, meaning like avoid having something that looks like this, where you only draw at one small part of the axis and have the rest of it is empty. It should be more something like this. Every graph has to have a title, right? And every graph has to have a number. So this will be diagram 1, and the title will be red and yellow dyes screen against the visible spectrum, right? The title should describe what I am looking at, which is the screen of the red and the yellow dye against the visible spectrum. Every diagram has to have a number that you refer to when you talk about, and it has to have a title, a proper title, right? These are the things I'm going to look at when I am grading your lab report. After that, you're going to start with part 2, And this is, again, you start with the objective. What is the objective of part 2? What we did and why we did it, right? We prepared multiple concentrations of the red dye and the yellow dye. Why we did this? So we can create standard curves and get the K values. Then we do have a procedure here, right? We did have to make our own stock solution. How did you make it? Remember, M1V1 equals M2V2. And how did you make the sub-concentrations from your own stock solution, also using the M1V1 equals M2V2? Then you're going to have the data. And in the data, remember, you're going to have 4 diagrams. And I want to see all of them nicely done with a trend line and an equation with Excel. Remember, this is absorbance versus concentration. Every diagram has to have a number, and it does have to have a title, okay? Then after that, I need you to create a table. And in this table, I want you to tell me for the red dye and for the yellow dye, I want to have the K values for the red and for the yellow, and I want to have them at both 400 nanometer and 510 nanometer. Now you are reporting again the K values. K does have units, okay? So let's figure out the unit of K. Absorbance equal KBC, meaning K equals absorbance over BC. Absorbance doesn't have a unit. The B is centimeter and C is millimolar. So therefore, the unit of K is millimolar, -1 centimeter, -1. It's very important that you include that. Okay? Now, after that, you are going to go to part 3. And in part 3, again, you're going to have an objective, which is, taking your unknown mixture and measuring the absorbance at both wavelengths, since your unknown has both colors. Then you're going to have a procedure and data. And you're going to show me here what was your unknown absorbance at 400 nanometer and 510 nanometer, okay? So you're going to report the unknown absorbance here. Again, absorbance does not have units. And then I'm going to have you put in a different section unknown calculations. And the first thing I need is, in a big square, I want to see your unknown number. After seeing your unknown number, then you do the calculation as I have explained them at the beginning of this video. After that, you're going to have your final conclusion about what is the concentration of your unknown in what is the concentration of the red dye in your unknown, so CR, and what is the concentration of the yellow dye in your unknown, CY, and I want to see that also in a small little table. That will conclude your lab report. Just note that your unknowns have to have a unit that's millimolar, and it has to be within the curve you tested, which means your concentration has to be anywhere between 0.1 millimolar all the way to maybe 0.99 millimolar, right? So if you have something different, it means you're doing something wrong. I wish this was a clear explanation of how we make the calculation and how we will be writing our lab report. Thank you, and I will see you in the next video.